Let me introduce you Professor Dirk Pleiter. I think he's the professor at KubeEdge, and he's also the director of the PDC Center for High Performance Computing. For people in HPC, he doesn't need an introduction, and personally, I think he's one of the nicest person you can meet, and I hope you all enjoy speaking to him. And please carry on. Yeah, thanks.
Okay, thank you so much, Karsi. So essentially the way of how we started to think about the day today is that we will start essentially with two lectures. I mean, one giving so a bit of background on the ARM ecosystem. So that's the ARM-based processor architectures. And then there will be, say, a follow-up on, say, performance. Already at this point, I'd say it will be a bit more general, and you will maybe be a bit surprised because there's so much talk about ARM that at some point there will not be so much about ARM anymore, because I hope I will convince you that ARM is just one, say, architecture which is not too dissimilar from other architectures. And then we will have the introduction to the Haiku cluster, so which is an ARM-based cluster, and that's where you also will get access. And that's where you can then start to play around with an ARM-based architecture, and then then the proof is in the pudding, whether you agree on that it's not too dissimilar with any kind of other architectures you have been encountering, which is most likely x86-based architectures. And then after the lunch break, we will then have, yet another lecture, which is more than geared towards optimization. I will take you through a few optimization techniques, but also here you will see it's actually more general than, say, really ARM-specific, right? Because at least for the Kunpeng, there is not, so much, ARM-specific one. You could, of course, talk about here and there some Kunpeng-specific optimizations, but that would be a bit too special. Please interrupt me at any point if you have questions. So I really prefer if it's a bit more interactive. Don't worry about interrupting me here. Okay, when talking about ARM, I will basically do it in three parts. The first part is I will give you a bit of a broader background in ARM. What is ARM? And what are also the misunderstandings and the myths behind ARM? Try to clarify this a bit. Then go in some of the bit more technical details when it comes to, also the ARM architecture. It's actually a little bit more than the instruction set architecture. And then I will finally, in just a few slides, take you to some detail of the processor, which is, the basic building block of the cluster where you will have access then later today. So let's start with ARM and what is actually ARM, because that's actually, there's a lot of misunderstanding, so that's why I think it's worthwhile clarifying it. There's essentially, three correct answers to ARM, and there's one which is typically seen as an answer which is the wrong answer. Well, let's go one by one. So the simplest answer is, well, ARM is just a company. A semiconductor and also a software design company. So they're actually doing also quite a lot of software design, and they also acquired, software companies. It was founded in the early 90s, but it did have, a longer background. It has still a headquarter in the UK. Also, it is by now a daughter company of a company which is called the SoftBank Group, which is a Japanese company. So that's why I'm saying this, sometimes it's currently quite popular to talk about, European companies. Then, of course, you can start to think or not think about whether UK is still Europe, but at least from an European Union perspective, it was already then considered as not being anymore, and a European company, and whether, a company which is owned by a Japanese company is still a European company. So that's why there is still, quite some debate, for instance, in the context of the European Processor Initiative, whether it should be based on ARM technology or not. So in the first generation, it should be based on ARM technology, but as some of you might be aware, there's also currently a lot of discussion on whether, at least the efforts which are, funded also by the European Commission should be based on RISC-V. So this is maybe something for a coffee break talk, not for a serious lecture. So let's go to the second correct answer, is that ARM is an architecture, right? And so it's this company is the owner of this architecture and is regularly producing updates of this architecture. And the architecture in particular includes an instruction set architecture. So an instruction set architecture is essentially, say, a list of, a definition of instructions which the processor is supposed to understand, right? Because that is something which you have to define, because how can you otherwise, say, have somebody else doing a compiler, because the compiler has to generate instructions, and then of course you have to have a good definition of these instructions for the compiler being able to produce these instructions. And there are, say, different types of instructions. So for those who have not, say, computer science background, I mean, I mentioned already, say, for instance, x86, which is, say, at least for, say, the desktop, but also for the server market, is still the most widely used instruction set architecture, but something which may change. You have maybe also, say, heard about, say, Power, which was, say, originally driven by IBM. Let's see what the future there is, but there's also ones which are by now, say, a bit less known, like Spark. So there is a number of instruction set architectures around, and also Karsi mentioned now a bit of a newcomer that is RISC-V. And they are, say, have been, because if you look in the longer history, there had essentially been a zoo of instruction set architectures, and they had at some point also been classified, as say good computer scientists do. And one way of say classifying is to actually talk, for instance, about so-called reduced instruction set instruction set architectures. Sorry for this very long word, but it was at some point there was say. A bit of, say, two philosophies. One philosophy was, okay, we should have very complex instructions which encode a lot of information, and then leave it to the hardware to decode this information and to do the right thing, right? So, for instance, x86 belongs to this class of the so-called complex instruction set architectures. Now, at some point, say another idea came up and say, well, no, guys, this is not a good idea. I mean, you end up with so many very complex instructions, but at the end, I mean, you can break it down, these instructions, into a number of smaller instructions. And in fact, if you look at many hardware, also in the x86 world, that's what the processor is doing, right? So it takes these complex instructions and translates it into a sequence of micro instructions, right? So these people said, okay, I mean, let's get away with all the complex instructions. Let's just reduce it and have simple instructions, right? And that's where then, say, also ARM has its roots. Even so, if you look at it nowadays, I mean, the number of instructions which are part of the instruction set architecture have become pretty big. So, I mean, in some sense, the distinction between, say, RISC and the complex instruction sets architectures is also a little bit blur. Now, the ARM architecture actually has a longer history than the company itself. It goes back to 1985, and since then it has been regularly updated, and quite recently it was now ARM v9, which had been introduced or launched in 2021. It doesn't mean that you immediately find then processors on the market which support this instruction set architecture, so there's still also typically one or few years delay until it really, say, becomes then visible in products, but that's essentially, say, the new direction then to go. Now, the third correct answer to what ARM is ARM is also just producing designs. So if you want to build a CPU, you can go to ARM, knock on the door and say, okay, I mean, I would like to use your instruction set architecture, and then I do all my design myself, right? What actually most of the companies are doing is actually they knock on ARM's door and say, okay, I mean, I would like to use your instruction set architecture, but I would also like you to provide me some design. So, for instance, the design for a processor core. So that I don't do it myself. I just take your design and then integrate it into a CPU in, say, a particular configuration, which is, say, the design of the CPU manufacturer. Or you might also add your own IP components, right? So that's how you can then generate a whole kind of diversity of different kinds of processors. And so I just put here one example, because here we focus, of course, not on the mobile market, where ARM is, say, the dominating architecture, but ARM has already since 10 years put quite a lot of effort in also entering, say, the server class processor market. And now a few years ago introduced a new core design, which they called Neoverse, and it has now already, say, 2 or 3 generations, and it has now actually quite a strong uptake on the market. So if you look, and I will show you some of the processors, which ARM processors, which are actually have become quite popular because there's very big companies behind it. They, for instance, use the new Verse V1 core. Now, coming to what is the wrong answer, and many people, if you say, okay, I mean, I'm talking about an ARM processor, and think about, okay, that's the processor from ARM. ARM is not providing CPUs as a product, right? It may they are building sometimes processors, but that's really more for testing purposes and for experimenting purposes. If you buy a so-called ARM processor, you buy a processor from another company, which has, of course, a contract with ARM, because they have to have a license from ARM in order to be able to use the instruction set architecture, for being able to maybe also use the core. So the processor where we say will deal with today, it's done, for instance, by a company called HiSilicon, which is a 100% daughter of Huawei. And so it's then, say, not ARM, but it's a company, HiSilicon, which does this processor, right? We'll see that by now, for instance, also, say, cloud providers like Amazon, they started to say, okay, it's great that we have a company which, say, produces, say, designs for or important parts of a design of a processor. Now let's glue all this together and do our own processor, right? And they have now their own processor, right? But you don't have a processor from ARM itself. Now, let's look where, say, ARM stands, and I just copied some figures from ARM itself, and that I didn't do too much effort in finding, say, the most recent numbers, but I think they are impressive enough. I mean, there are figures from early 2021, and so, I mean, what I said was that just in the last quarter of 2020, I mean, it was almost 7 billion ARM-based chips which had been shipped, right? So it's not ARM who shipped it, but it was basically all the licensees of ARM who shipped that. And you can also see here in this picture, I mean, it has seen quite a significant growth. But what is also interesting to see is the number of licensees is not too big. So at the end, it's in some sense, say, a small market, in the sense of that, say, ARM is dealing with a rather small number of companies. And if you look what are, say, the really big players, and then it's even, say, much less than these 530 licensees. But what I think is also interesting and makes this architecture interesting is that, I mean, ARM really started, and that's where, say, part of the myth also came from, started really in the low power section in the mobile market, where it really started to dominate. And but now it is, say, getting, say, into more and more different devices. And also what is interesting for today is, of course, in the HPC sector. But Karsi already mentioned also maybe some of the things which we try to address also in OEHI is the compute continuum. And that's where it also you start to look, okay, I mean, how can you couple, say, something which is in a cloud data center or in an HPC data center? How can you connect that all the way to, say, something which is on the edge and which is also in the IoT sphere, right? And if you now have technology where you can use it, say, basically in, say, the full continuum, that makes it, of course, quite attractive. Now, where does it stand with the ARM server class CPUs? Now, it was actually quite a long endeavor until, I think, by now one can really confidently say that ARM really made it into, say, the market of the server class CPUs. But you can still see it's very much, say, an up and down. And I put you here just, say, a number of examples. And many of them, I mean, or a number of them at least, have also been used in the HPC context. For instance, Marvel Thunder X2 had been, say, quite a successful one and was also used for, say, first HPC systems which had been listed on the so-called top 500 list. So that's a list where we look at the different supercomputers according to their performance when they execute a specific benchmark, which is the high performance impact benchmark. May argue, oh, it's a good benchmark at least, but it allows you to do a same comparison. And that was, say, one of the first one with, say, a system in Sandia. And it was, say, launched in 2018 in a very interesting manner. Because it was moving also from one company to another company at that point. actually a very nice process from design-wise, but unfortunately they didn't really make it on the market. A follow-up like a Sander X3 and a Sander X4, which was all in the planning, has so far never materialized, and it's a bit unclear of how Marvel, say, wants to continue with this processor. So it also shows you that even if you have been once, say, quite successful, and let's say pushing things on the market, it doesn't mean that it's really sustainable. The second example, that's say the example where we'll also look at a little bit more in detail later, and we also will say have access to the HiSilicon Kunpeng 920, which was launched not so much later. I mean, I think in particular in the Chinese market had quite an success, but unfortunately it had the bad luck of now entering into this geopolitics situations, and therefore did not have, say, as much attraction as one would expect. And then the next one, the Fujitsu A64FX, is a very interesting processor. It's actually shown here, because this was the processor which was used for a Japanese supercomputer, and it was actually designed really for this supercomputer in a co-design effort, where this supercomputer really made it onto position 1 of the top 500 list, right? So it was really, say, possible to make something extremely fast, and that was because it was really possible to use basically this flexibility which has in this ARM ecosystem in order to design, say, a processor which was really suitable for the HPC market. All the other processors which are listed here, I mean, they are not designed for the HPC market, which is a rather small market. I mean, they just, in some sense, happen to be, say, suitable to some extent for the HPC market, and then the HPC market takes it. But the Fujitsu A64FX is really designed for the HPC market, and you can see it, for instance, it was one of the very first CPUs which used a very fast memory technology, so-called HBM technology, which is also used for GPUs. Because many of the, and we will come back to this point, many of the HPC applications actually are not so much in need in getting, say, a maximum number of flops, but actually being able to move data as fast as possible between the memory as well as the processor. Right? And it's now only now with the latest generation with Intel CPUs, where now Intel starts to do something similar. And that is, say, quite a number of years later, because they also quite delayed. Now, after that, there was a little bit of a cut, and now we see, say, a very significant uptake of ARM-based processor architectures, and that's not necessarily from an area where you would initially have expected that. I mentioned already that Amazon has its own processor, so that's a process which you can't buy, right? You can only buy access to an Amazon instance where this process is being used. And that is a clear difference, say, for some of the others. I mean, also, while HiSilicon doesn't sell it, they also use it yourself, but at least you can buy a server so you can have this hardware in your basement. You can't have a Graviton 3 in your basement, because you always have it somewhere in the cloud, right? That's their business model. But there's also now, say, smaller companies. I mean, in Silicon Valley, it's Ampere, which was not that well known, but also they leverage basically now the new opportunities with having, say, fabless designs. So basically, it's a company which doesn't have its own fab and buys quite a number of IP blocks then from ARM, and then creates another processor. And a more recent one, I mean, even so, it has a longer history in that company, is NVIDIA. I mean, NVIDIA has already since, I think that must have been about 10 years been working on ARM-based designs. They did it in particular also, say, in the more, say, mobile part, they had this takeout line, but they were already early thinking of having something more powerful. But it's now becoming, say, reality with Grace, which looks a very interesting, say, processor architecture. Unfortunately, well, it's also this company. The picture is a bit difficult to see, but it's interesting from the integration perspective, because you can basically, this is a building block with 2 CPUs, and you have to buy this full building block. But it has a number of nice features. And last but not least, I put here also Cyprel. Cyprel is the company which had been, founded on initiative by the European Commission with the mission of putting now a European server class processor in place. Now, I have a bit given up of, say, putting any kind of guesses on when they might come up with their first design, and they never disclosed the number, of course, they will have in there, so that's why I put two question marks, and we will say have to see what is actually coming there. Now, hardware looks pretty good in some sense, right? I mean, you have, say, as you can see in the previous slide, you have a choice between different processor architectures. They are very interesting and very powerful designs there. So that looks good. But what is often underestimated is the software ecosystem. And that actually has been, say, the biggest struggle for getting ARM into, say, the server market. And it took more than 10 years to get to a reasonable point, and I would still say we are not fully there, right? And so if I put my supercomputer data center director hat on and say, okay, ask myself the question, okay, could we switch, say, our HPE Cray system in our basement off and replace it by tomorrow by an ARM-based system? Then the simple answer would be no. And the reason for that is that while we have on our system, say, a lot of scientific applications where, say, many have been ported, so that would not be my worry. I would not have any sleepless nights. But the problem is we have, because we also say say technical university and we also collaborating with companies, we have a lot of, say, so-called ISV codes. So that is, ISV stands for independent software vendors. So there are companies which are designing software, and they are particularly strong when it comes to, say, industry-grade software, also in the area of computational fluid dynamics. And this is the kind of software which we use in our system. And here, the current status is very few are available. Now, I consciously used the term here, available. I didn't say very few have been ported. They have been ported, but for an ISV to put these codes, I mean, it's not an open source code, right? So for making them available, it also means that they have to basically decide on whether they provide support for this one particular kind of version of their software, right? And so far the decision was, well, no, there are too few customers which would like to run it on ARM, so we're not going to do that. Now it will be very interesting to see. I mean, that's really where we still need the phase transition. I would say people start now to become a bit more optimistic that this phase transition is ahead of us. and probably say big players like Amazon could play here an important role because we might also see that the ISV codes, which today might often be run on, say, on-premise cluster, might in the future more often be executed in the cloud. And if you have then a cloud provider like Amazon, and those other cloud providers are looking at ARM-based architectures, then of course the commercial situation for the ISV starts to change, and that may actually then induce the phase transition, right? So you can hear this very nice example where, say, it's really economics which drives the technical evolution, right? It's not just, say, the technical excellence. Otherwise, I mean, when it comes to, say, compilers, there are several choices. So I think here the situation is quite good. Also with numerical libraries, I mean, here and there are some gaps, but say the most important one, they have not only been ported, but they also have been optimized for different ARM-based architectures. And for instance, also Stepan, who is here with us, I mean, he has also been, for instance, involved in optimizing one of the numerical libraries for linear algebra. Also with the operating system, things look quite good. I mean, there are various Linux distributions, and there the support is quite good. In particular, it also includes, for instance, the two important enterprise versions, SUSE and Red Hat. So that's quite good. Where I would still have a bit of a concern when it comes to parallel file systems. So here the support is, I mean, it runs. Stefan can tell more what it means, more or less, but it's really, I mean, these are extremely complex beasts, and even so, some of them might be open source. I mean, it requires, again, the support by companies, and if the market is too small, there is basically no good support model for that. And that's the situation which we have. So that is really something which I would still see as a kind of an often concern, one of the major concerns when it comes to deployment of large-scale ARM-based clusters. Still, I want to make a case for ARM, and that's repeating a bit of what I've also been saying, because I think there's good reasons to think about ARM as being something which is interesting, particularly in the HPC context. And it has a lot to do with that the ARM business model relies on that there are several competing solution providers. Right, so you basically have one company which is just providing, say, the intellectual property and the designs. But then when it comes to products for, say, then also end users or other customers, it is basically a bunch of companies, and they compete with each other. And this is a good situation, at least if you look in the HPC context, because with competition, you have also a chance of getting better prices. I mean, that was only recently changed a bit, but till a few years ago, if you want to do say, a large-scale HPC cluster or supercomputer, well, you had no choice but go for Intel, right? And of course, the prices for these CPUs was pretty high, right? So, and it was really, say, the CPU price was dominating, say, the cost for a supercomputer. And if you have more competition, and then there's a chance of these prices go down, and then you can rebalance also a bit the different cost components with an HPC system. For instance, spend more money on the I/O subsystem, more money on the network, etc. But it's also about the promotion for better solutions, right? Because I mean, if all these say solution providers would essentially do the same thing, I mean, yeah, I mean, that's of course not going to be very efficient, and at the end you would only have one which say survives because it just has the power in, say, sustaining, say, a competence for say competition for prices. But at the end, I mean, it's also you can only sustain it if it's a competition for better solutions. And better solution can mean, say, an optimized solution for some segment of the market. And already provide this example of the A64FX processor, which was specifically designed for the HPC market, right? So if you would run, say, more general cloud type of workloads on that, like a database, you would be, say, very disappointed about the performance of this processor. So I would argue, okay, it's a great processor because it gives you a lot of performance, but it's performance for say, a typical set of HPC applications, not all HPC applications. And within this ecosystem, I mean, there's a lot of ways of how you can differentiate, right? I mean, you can say, for instance, have a different number of cores. You can, for instance, say, okay, I mean, I go for, say, a larger number of cores. And by the way, that I didn't point it out explicitly, but it's one of the interesting to observe is in the market of ARM-based processors, I mean, typically the core count was significantly larger than what you see, for instance, for the processor from Intel. Intel made a bit the design choice, okay, we go for very fat cores, a few of them. Here the choice was more going for a larger number of cores. And I mean, even that has, I mean, today you can find, say, 32 core processors of Intel. But here we talk about a processor in 2018, right? And now the market has already, say, processors with 128 cores, right? So that's really, say, something where you can see there is a bit of a difference in the strategies. And you can here also then play a bit in what is the performance per core. I mean, if you mainly focus on floating point operations, I will introduce you to, say, vector instructions, or actually I will call them SIMD instructions, and you can, say, use them with different widths. That's, for instance, how you can see also a difference between today when you look, for instance, in x86 processors from Intel and AMD. Intel supports AVX 512, so it's with 512-bit wide vectors, while AMD only goes to AVX 2, which is then only with 256 bits, right? So also there you can differentiate a bit, but here you can even differentiate more, as we will see. But you can also do a lot of things with the memory hierarchy, and what we will see in the future more and more coming is also in terms in differentiating with, say, for instance, accelerators, which you integrate into your processor design. Now, let's also, say, go to the full things about ARM, and it's a bit this history of having, say, low power designs, right? That's meaning that you have, of course, if you want to have an ARM processor in your mobile, and most of the mobile phones have an ARM-based processor, I mean, of course, you can't have something with a thermal design point of 200 watts, right? Because you don't have it in your trousers anymore. But you are forced to do it on a very low power, but that typically comes also with less performance. Now the question is, where do we stand with performance, power efficiency, right? So And if you look there, and that is really, it's not surprising, is you see basically quite a lot of variety. I mean, I showed here 3 ARM-based processors, so the A64FX from Fujitsu, Sonnet X2 from Marvell, and the Kunping 920 from HiSilicon. And if you look while you run this high-performance impact benchmark, if you're not only looking at the throughput of floating point operations, but if you divide it additionally by the power consumption, so you have something in units of gigaflops per second per watt, then you have a huge range from 3 gigaflops per second per watt to 70 gigaflops per watt, and that's where you have, say, a reasonable recent version of Intel CPUs. And I mean, I never understood why people believe that ARM is say, more power efficient. I mean, of course, you can gain a little bit by, say, the RISC instructions. You spend a little bit, say, gates on, say, pre-processing the instructions. But it doesn't make so much of a difference when it comes to, say, a high-performance LIMPAC. So at the end, it is about your design, right? And at the end, after whatever instruction set architecture you're using, I mean, you're doing a design with the CMOS technology, right? Say, most of the technology which is in your processor is the same, right? Whether it's an Intel or whether it's one from the other vendors, whether it's x86 or whether it's ARM, right? And so you can explain a bit the difference. So, I mean, Kunping doesn't look that good in this picture because this is now for the power efficiency when running, say, high-performance LIMPAC benchmark, right? I mean, the power efficiency when running other workloads looks much better. But this process has not been optimized for floating point operations. So that's why this figure looks actually quite bad. Just a few different design choices, and this figure could have been looking much better. But it was a design choice. I mean, you have to make trade-off decisions, right? And actually doesn't look so much worse than compared to the Sonnet X2. Now, that the Xeon is much better is because it has been much more optimized for floating point operations. So it has much more powerful cores, and so that's why the balance becomes then is more in that direction. And it becomes even more extreme for the A64FX, which is really a very much specialized design, and that has also quite some consequences, and also makes the performance of some applications rather bad. Because, for instance, it had very deep execution pipelines, and to keep these pipelines safe filled is a challenge for a number of applications. But of course, it allowed to make a design was really very much optimized for power efficiency, and that allowed with this processor even to get to a design which catched a number of people a bit by surprise, come up with a design which was more power efficient than GPU-based designs. Because since quite a number of years we are used, when we look at the so-called Green 500 list, which is basically the sister of the top 500 list, it's just instead of looking at the throughput of floating point operations per time unit, it looks at the throughput per watt, and so it's basically a bit of a reordering. And now for quite a number of years, essentially since IBM stopped Blue Gene, it was all dominated by the accelerators. And then suddenly, say, a more standard like processor design made it to the top of this list. So be careful of thinking about ARM necessarily being power efficient. It depends on the specific solution. Now, let's look a bit into the instruction set architecture. I mean, I said already, it's a RISC instruction set architecture, and it comes with, say, compared also with x86, with a relatively large and uniform register farm. So all the instructions essentially take their operands from the same register farm. And that is another differentiator, for instance, with x86, it has a so-called load store architecture. And that means that whatever you do, I mean, all the data processing operations, particularly all the floating point operations, they take their operands from the register file and they store things back to the register file. And if you want to have something out of the memory or you want to put something back into the memory, you have to put an explicit load or store instruction. Right? So that is, say, typical for RISC instruction set architectures, that they are so-called load store architectures, and unlike x86 where you can have, say, one operand can be a reference to the memory. Now, since ARM has still, say, very strong footprint in the mobile market and in the embedded market, I mean, it's not necessary to have everything 64 bits, so you still have 32-bit execution state, but for us, in this context, of course, only the 46-bit is relevant. And I will explain a bit later what it actually means. So-called SIMD instructions are now part of the instruction set architecture. They had been added relatively late compared to, for instance, x86, where already say in the early 2000s you had SSE, but it's now part of the standard. And it also supports multiple architecture profiles, so you can use ARM designs for microcontrollers, also for real-time designs, but for us only relevant is what is the so-called application profile. Now, ARM is not, say, very static. I mean, I talked already, say, about that you have these different generations of the ARM architecture. We are now at the 9th generation, but also once this generation is released, then you have, say, sub-generations, but then you have, additionally, you also have extensions. And this is in parts also to give you more flexibility, so that somebody who wants to use an ARM design can say, okay, I want to have the ARM design with this or that extension. Or I don't want it because I don't need these capabilities. So, for instance, some of the extensions which have been, say, are available in ARMv8, sometimes they are optional, sometimes they are just added in the sub-generations. For the HPC part, and I will explain a bit more detail, a very interesting one is the so-called scalable vector extension. So that was the addition of yet another type of SIMD instructions which supports, say, a very wide operands. What might become a bit more interesting also, at least for a data center, is the cryptographic extensions. Also security does start to play more and more a role, in particular also by being able to run, for instance, say processing of GDPR protected data in our systems, then this becomes interesting. RAS, which stands for reliability, availability, and serviceability, is obviously something important, and also there in the case also of the feedbacks from the data center is getting, say, better in terms of adding control and status registers, so that you have a better understanding, okay, is there, say, some processor which is somewhat getting weak. And what is also nice, I mean, we'll touch also later on today, I mean, this question about how do we actually, say, measure, say, performance, right? And having, say, support from the hardware there is something which is extremely helpful, and also there we have, say, changes in the ARM architecture. Now, I mentioned already, say, several times the keyword SIMD, and I cannot assume that all of you, say, know what SIMD actually stands for. Well, SIMD actually goes back to a more general classification of parallelism in computer architecture and stands for single instructions, multiple data. So the idea behind that is that you could have parallelism by saying, okay, I have just one instruction, but this instruction is operating on multiple data. If you look at it in a more mathematical way, so let's assume we have two vectors x and y, which have 4 elements, and I would like to implement this operation where I add these 2 vectors with just a single instruction, right? And these are called SIMD instructions. And the benefit of doing that is that that now I only have to deal with one single instruction. I have to spend only, say, the effort in managing this one instruction, and I do several operations. So in this case, because I'm adding with just one instruction, I'm doing 4 additions here of x0 plus y0 all the way till x3 to y3. So I do 4 floating point operations, but only with a single instruction, right? And there are quite a lot of applications also in the scientific world where this is quite beneficial, but it can also be a challenge to reformulate the application such that you can map it actually onto these kind of SIMD instructions. I mean, just to be fair, I mean, HPC was not the driving factor for getting the SIMD instructions in place. I mean, that were more, say, graphical applications and multimedia. So, I mean, earlier ones were also called MMX for multimedia extensions, right? But by now, I mean, whatever instruction set architecture you look at, I mean, they do have these kind of extensions. So one of the first one was in x86 where introduced SSE. That was then later, well, to some extent replaced by AVX. And while SSE had a width of 128 bits, AVX and AVX2 were 256 bit. So if these were, say, double precisions, then it were, say, you could have 4 times 64 bit, gives you 128. So this is an operation which you can basically with one instruction AVX and AVX2 implement. AVX 512, I mean, as the name says, is already 512 bit. So we have vectors of 8 doubles or 16 single precision floating point operations or 32 half precision floating point operations. So become already quite long vectors. Power was, say, quite conservative, so they didn't make it yet beyond the 128-bit. And ARM, well, in the 7th generation, Neon was added, which became basically integral part of V8, but then in V8, SVE was added. And SVE is now quite interesting. I mentioned already, stands for Scalable Vector Extension, because at least, say, the specification says it could be up to 2048 bits. Well, I haven't seen anybody to even think about 512 bits, and my prediction is probably not so likely of getting beyond the 512 bits, but it does have a number of interesting features. And what is really unique with SVE is a feature which is called vector length agnostic. So it is an instruction set architecture which doesn't prescribe the width of the vectors. And that is very interesting if you think about it, right? So it basically has the approach to say, okay, I mean, you can say produce an executable, and inside this executable, it's completely unknown on whether it runs on a hardware where I have SVE pipelines with a width of 128-bit, 256-bit, 512-bit, or in theory 2048 bits, right? And so it really supports that. But in order to do so, I mean, of course, you need to have really a very suitable definition for the instruction set architecture and be able, I mean, to have also, say, the hardware support. Now, what I would claim is, but of course, how much benefit you can actually get from that, it depends a bit, but at least it simplifies, say, a lot the, say, the software. And sorry for, but I think it's, from time to time, I dive a little bit deeper, and now I dare to dive, say, a bit to the assembler level. But I try to do it such that I hope all of you, even those who have never, say, looked into assembler, can follow, and maybe it's a bit of an incentive of sometimes looking into that. Let's look in a very simple application, DAXP. We will come back to this application later on. So DAXP is something which you find in all standard numerical libraries, which essentially D stands for double precision, and you have A times X, where A is the scalar, X is an array, plus Y, and Y is also then an array. And so if you write it just in C, I mean, we just have here a for loop, and we have here Y plus equal A times X, right? So we have, say, two input vectors, X and Y. We scale X by A, and then we add these two, and then overwrite Y. So that's the standard definition of DAXP. Now here, what I did is I used, it's not even anymore the most recent version of GCC, and I told him, okay, please take this C file and compile it for ARMv8 plus SVE. So I left everything completely to the compiler, plus I said, okay, I would like you to really optimize it. And what the compiler, say, returned here was really, I mean, you can at some point maybe just look at what say you would have for x86. I can promise you it will look much more complex. It comes back with a very simple code. And I mean, of course, it's not always that easy to read it, but I mean, if you have a construct like this, I mean, my tip is try to see whether you can find back the loop, right? Because I have here just a single loop. And what I have here is here a label, and here I have a branch which refers to this label. So I can quickly guess this is my loop body here. And what do I see happening here is I see here a load and here a load. That's more or less what I would expect, because I have to load X and Y. Now, I have to multiply X with A and add Y to it. So what I see here is now a fused multiply add. So I have the multiplication and the addition. So basically it's now this part which is implemented in this instruction, and then I have to store because I have to store Y. So I hope that I can convince you that here you can, bit by pattern matching, find back in what is our original C program and what is in the assembler. Now let's look a bit more further. The next instruction which we see here there's an increment. So that, and that's also what we expect, right? Because we have here this loop variable, which is incremented. But now, and that's of course not so easy to recognize, I mean, these instructions here are vector instructions. So it's actually not doing, say, only processing one element, but actually in one iteration, it's executing multiple elements. But the compiler doesn't know how many of these elements. So it relies on that the compiler could just say increment. And the hardware knows by how much do I have to increment, because that depends on, say, the hardware. Do I have something where I have support for 256-bit or 512-bit? And so for this, I mean, it requires, and then of course there's some subtlety here, is that I don't know whether n is a multiple of these vector widths, right? So it could be an odd number, and typically say the width is an even number, right? So for this, I also have to operate in something which is called predicates, and that is also, say, implicitly updated here in these instructions, so that possibly in the last instructions, you still do a vector operation, but not all parts of these vector instructions are then actually written back into the register file. Just to take into account that maybe only a few elements of the vector are still active. So you can see here, I mean, there's still quite some smart things which you can do, and so it's good to have this competition in the instruction set architectures. Now, just a final comment before I get into a little bit of detail on the comping processor. Just one last part which goes actually a bit beyond the instruction set architecture and makes clear we're not just talking about an instruction set architecture, but we're talking about an architecture which includes, for instance, also a memory model. And that's also where there is a clear difference between x86 and ARM. So ARM, and that's where ARM is actually a bit more similar to Power. They both have a so-called relaxed consistency model. That means that they are less strict in making promises in which order, if you have a multi-threaded application, so on a processor with multiple cores, in which order write instructions, so stores and loads are seen. Let me just, I mean, without getting into too many details, but it's just more to convey the message that there are differences between architectures. Take you through one, say, textbook example. Let's say, okay, we have a thread 1 and we have a thread 2. Okay? And thread 1, say, initially it has a variable a and b, which, say, if you think about C conventions, they initially are static variables, they are initialized with 0. So initially a has the value 0 and b has the value 0. And then at some point, an expression comes here and says, okay, assign the value 1 to the variable a. And then we continue with doing b here. And now there's a second thread, and now we don't have any explicit, say, synchronization here, so basically a lot of things could happen, which takes the value of b, which is, say, overwritten here by thread 1, and puts it in R1 and a in R2. Now, of course, since there's no synchronization, you don't exactly know what is the value in R1. But let's assume that we would see, after we run this experiment a number of times, can it happen that we see R1 being 1 and R2 being 0? And the reason why this is not so obvious is, you would say, okay, if I, say, load B into R1, and I get a 1, and since B has been written, the 1 has been written to B after it was written to A, I would expect, since the assignment of B to R1, the assignment of A to R2 happens after B has been assigned to R1, that if I observe R1 to be 1, that I observe R2 also to be 1. For x86 it would be the case. For ARM not. And that has to do with this relaxed memory model that, say, even so in a single thread, say the order of the write operations is preserved, but then when it comes to how this is visible to the other threads, this is not guaranteed anymore. So the order of the write operations here doesn't have an impact here. And that's why you can actually there is, say, the possibility that you might actually observe these values. For ARM, also for power, but not for x86. x86 guarantees you that you would see, say, these write operations in the right order.
Like what makes it to choose between 0 and 1 for R2?
That's essentially a question of hardware implementation. I mean, this is just a question of timing, right? I mean, of course, if you would have a proper synchronization in place there, I mean, of course, you can prevent this from happening. But it rather tells you that if you really rely on this to happen, then you have to put, say, the proper synchronization mechanisms in place there. And that's where, if you want to port things to ARM, you might have to actually do really something to change something in your code. Where something is more or less because the memory model is guaranteed in x86, but it's not guaranteed in ARM anymore. I mean, it doesn't say, I mean, when I say here that when I ask the question, I mean, could this be observed, right? It doesn't say that for each processor, it's definitely guaranteed that you observe it, right? It's just that the architecture doesn't say guarantee that you cannot observe this case. And yeah, I mean, how do you know that? Maybe in a very small probability you will see that, right? I mean, that's the typical thing which if you parallelize it and you have somewhere a race condition in your program, I mean, it might like look perfectly in a small number of cores or a small number of nodes, but then you scale out, timing changes a little bit, and suddenly you see that the timing is such that the order does matter. Right? So that is then, say, wildlife. That's essentially the warning. You are here in the wildlife. Anything can happen. Okay, to conclude this part, say very briefly just something about the Kunpeng 920 processor. It comes, I mean, that was already highlighted earlier, it comes with, say, a pretty large number of cores. So I mean, it came out, I think, as more or less at a similar time, like also AMD EPYC came out with, say, its first versions with 64 cores. So it was pretty remarkable to have this on the more standard CPU side. I mean, of course, there had been Xeon Phi already earlier. And HiSilicon did here a bit of an approach, which we also find, for instance, in the AMD processors, instead of having, say, one big chip, using, say, several chips. And they didn't go to the same extreme as, for instance, AMD did. AMD uses now, say chiplets with just 8 cores. Here they use, say, larger chiplets. So if you look in the HPC version, which you also will find in the cluster, we are actually talking about CPUs which have 2 compute chiplets and 1 I/O chiplet. And this has become a bit of a more standard approach in industry. Well, there's probably still some people which are think, okay, one big die is a good approach, but my guess it will be more and more about in the future about chiplets. It also has some benefits of that you can say, okay, I mean, for the compute chiplets, there I need to maximize the number of transistors, so I go for a very advanced, say, silicon technology. So that was, for instance, done in 7 nanometer TSMC, while for the I/O chiplet, I can relax it and go for, say, a bit coarser chiplet. And you see exactly AMD, for instance, doing exactly the same in the EPYC, right? So you have a number of these compute chiplets where you have the CPU cores, and then you have, say, the one which is more for the I/O, for the external memory attachment, and there they also use, I'm not sure, I don't remember exactly what it was, 16 nanometer, but it's definitely also not a 7 nanometer. But of course now you can, say, produce also larger chips because you basically put I find it interesting that HiSilicon use here, say, calls the Lego style architecture. I just quoted from a publication, but you can think a little bit in terms of, say, a part of a Lego architecture because you have essentially an interposer and you put different Lego bricks on top of it. I don't like this picture too much because the interface between Lego bricks is much simpler than the interface between, say, these chiplets and the interposer. But of course, it gives you, say, more flexibility. You can build, say, larger chips, and that's what we now see in the market happening is that we now start to have CPUs with more and more power consumption, right? So, I mean, we now, already 200 watt is pretty much, but we will see in the future, say, a few hundred, even more. So it might go to, say, 400 watts. I would not be surprised. And that, of course, has some impact on the design. But let's stick with the Kunpeng 920. I mean, it's general otherwise, I say, a very standard processor architecture. I mean, starting, say, from the core, so it has, you can basically decode 5 instructions per clock cycle, so that gives you an upper limit of how many, instructions per cycle you have. Then it has a SIMD units for actually doing 32-bit neon instructions or 64-bit neon instructions. And that's where you can see here where there's not an optimization for floating point operations. It only has one pipeline for 64-bit neon instructions, right? And that gives also is a bit the reason why this figure for the power efficiency look a bit bad. So we have only one neon instructions, so that's 2 times 64 bits. So we have 2 FMA per clock cycle, which then translates into 4 flops. For the 32-bit, we have here 2, and now we can fit 4 times 32 in 128 bits, so that's why we have 2 times 4 FMAs, so that gives us then 16 flops in one clock cycle in the maximum throughput. And then from the cache architecture, it's very standard. I mean, you find in a lot of other architectures something around the 64 kilobyte level 1 data and instruction cache. I mean, the level 2 is, say, pretty large. You have, say, architecture with less size. And now these 4, say, CPU cores with the 4 private level 2 caches, they are now integrated into one cluster. And each of these clusters is now connected here to a ring bus. And we have now in one chiplet, we have here 4 on this side and 4 clusters on that side. So we have in total, we have 8 of these clusters. Each cluster has 4 cores, gives us 32 cores. Additionally, and that makes it also very interesting, is that there are 2 memory controllers on this side and 2 memory controllers on this side. So we have 4 DDR channels for one chiplet. Now, remember that we have 2 of these chiplets, that gives us 8. So also there, Kunpeng, when it was introduced, was ahead of the market because, for instance, Intel at that point had still only 6 DDR channels. Just very briefly, just to show that it's also there's the I/O chip where you have, say, for instance, all the PCI Express and the Ethernet and even, say, disk interfaces. So you can see here, this is not something for HPC because you don't need a SAS interface for an HPC, at least for the compute part, but in a cloud system, that's of course interesting. Then final slide, just look a bit on the bandwidth. So if you look at the bandwidth to the level 1, we have 2 times 128 bit per cycle, and if you multiply it with the 3 gigahertz clock and the 64 cores in the 2 chiplets, then we have a quite impressive 6 terabytes per second bandwidth to the aggregate bandwidth to the level 1, and there's a similar bandwidth to the level 2, but then to the level 3 it's very much reduced because that is essentially limited by the capability of the ring bus. And then say in terms of if you look at the external memory controller, and take into account that it can be, say, 2.9333 gigatransfers per second, multiplied with the 8 channels, you can easily derive that, say, the theoretical upper limit for the memory bandwidth is 191 gigabytes per second. Now, we can also see here the typical memory hierarchy in the sense of that when it comes to the latencies, the level 1 is just with a few clock cycles, so we are here in the order of a few nanoseconds, already twice for the level 2 and significantly more for the level 3. But these are, say, very typical figures which you also find in other architectures, and that you are, say, somewhere in the order of a few hundred clock cycles or 100 nanoseconds for the external memory bandwidth. So, because we are essentially doing, say, very similar technologies, right? So there's no difference with any, say, processor which is not using ARM. Let me just conclude. I will show you for all 3 lectures a picture. I mean, there's a view on the Fugaku system. That is actually, say, the system which uses the A64AFX processor at scale. And with this system, it was possible to get on the first position, the top position of the top 500. It's not there anymore, but it's still, say, a very interesting system because it was really also a very remarkable process from the very beginning when this project started in the early in the early 2010s, it was really kick-started with a very scientific goal in mind. So it was really positioned as a science instrument. There wasn't really a thought about, okay, what is the kind of science which we want to have on this system? Something which I unfortunately don't find in many other regions, a little bit in the US, unfortunately not that much in Europe. So that's is really, I think, a bit of a weakness, and which makes the system very much interesting. Okay, thank you so much for taking attention for the ARM-based. Are there any questions? If not, then maybe let's, yeah? Sorry, it's a bit difficult to...
You just mentioned that ARM is not anymore in the Kubernetes system. So
It is used in ARM. It's an ARM-based system.
It is not the first one on top of everything.
It was not the first one which was on the top 500. So there's actually, say, systems with the Sundrax 2 were a bit earlier. Yeah. Okay. So after we have really focused very much on ARM, I will actually now in this second lecture be a bit more general about, say, performance analysis. Because as you have seen already, say, in the hardware, I mean, a lot of things are not necessarily that much ARM specific. And I will do it in two parts. I will say first have something which is really much more generic about performance, how to think about performance, how to understand performance. That's actually what I really try to convey a bit, and then which we also you will have a chance to look at in the context of the say the hands-on, and then getting more practical. How can we actually measure performance? So. I mean, one of the problems a bit with, say, the performance is it also tends a bit to be a marketing number, right? So everybody wants to have a lot of performance, right? Whatever that means, right? It has to be a big number. So we have to be a bit careful and really try to see what do we mean. How do we define performance, and because only then, if you start to become more precise here, we can start to think about, can we understand our performance? And even though at the end it boils down to something very simple, I mean, like saying, okay, performance is divide the amount of work between the time it needs to do the work. It quickly gets a question about, okay, what how do we define actually these terms? And I mean, with the amount of work, that is already, say, often a bit of a problem if you look at also in scientific publications, right? I mean, that people are not necessarily very precise about what is the work which you have been executing, right? Which in fact is not good scientific practice, right? Because you could look at it as an experiment, and an experiment should be reproducible. And as such, scientific publications contain all the information which allows you to reproduce an experiment. But computer science is catching up there. So, I mean, there will be, say, more stricter, say, requirements that you also provide, for instance, more information when you do a publication, which allows others to reproduce your results. But the more challenging part, and that's what we also talk about a bit more, is, say, how to actually measure the execution time. Because that is not that easy to define that. And I will give you, for instance, here 2 examples and try to argue why both of them are reasonable, good ways of arguing it. One is called, say, the wall clock time. So that's essentially the time which it takes to execute your application. So you could think about it, say, in a more cartoon way. Well, you press the start button on your computer, you press start on, say, on your watch, and then when you see, oh, application ended, I again press, say, on my watch, and I stop, say, the counting. Now, the problem here is a bit that if I have, say, a computer like this one, but the same happens also, say, on an Android phone. I mean, this is, say, on my CPU, there are a lot of different threads and processes running, right? So I'm not only, say, busy with my work, right? And so if I could look exactly into the CPU, I will see the CPU busy with other things, right? And I might argue, okay, I'm not interested in when the CPU is doing something else and just, say, processing interrupt. I just want to know how long is the resource, say, the hardware resource occupied, right? Now, the resource occupation time will typically be smaller than this wall clock time. But you could argue, say, okay, I mean, it's maybe the computer architect which is more interested in the resource occupation. There's something a bit more clean lab. But maybe you as an end user, I mean, you don't care the resource occupation. I mean, you want to get the work done, and only when the work is done, I mean, it's finished for you. So you might be, say, much more interested in the wall clock time, right? So you can argue for either of them, and both is in some sense valid, and a valid thing of entering into this definition of performance. It's more about saying, okay, I mean, what do you mean with performance when you describe performance? Now, let's go a bit in some of the generics of computer architectures, and it's really indicated. I mean, if we look in high performance computing, actually a lot of our applications, not all, but at least a lot of applications, they are more suffering by not being able to move the data through the system fast enough. And actually, in the next 10 slides, it's largely, say, centered around, say, this question. And therefore, I also want to look a bit more carefully in, say, two other terms. One is called bandwidth, or equivalent throughput, and the other is latency. So what I mean in the following with bandwidth, I essentially, and this is a very simplified computer architecture, I look at an interface and I look, for instance, I count how many data per time unit is passing this interface. And this is what I call, say, then bandwidth. I could also have here a processing pipeline and then look how many instructions to pass here, and then I would have more, say, the throughput, right? But that's both is fine. One important thing as a takeaway, again, for good documentation is in many publications, scientific publications, you don't find this interface being defined, right? So again, it's very difficult to understand what is actually meant in this moment with the bandwidth. Bandwidth only gets proper definition if I define, say, the interface through which I, say, move data. Now, as we will see also a bit in a simplified example, is there is a difference between, say, bandwidth and latency, where latency is, or sometimes it's called in literature also response time, indicates basically time which passes when I start something until I end something. So for instance, if I would have here, say, this very simplified architecture, I would have, say, a processor core which requests data from memory, and then here the data is returned. Now, obviously, I mean, it takes some time until the request arrives here at the memory and before the data comes back, right? And then once the data starts getting back, then things are dominated by the bandwidth. But I have a part, when I look at the overall latency, I mean, I have to take into account that there is something where not so much is actually happening in terms of data transport. And this is also something which is, say, looked at in the so-called latency bandwidth. Yeah.
There's a question online. He or she wants to talk. Ghazal, you want to ask the question?
Yeah, sure. Do you guys hear my voice now?
Yes, we can hear you.
Oh, that's great. Professor, if you could just please go to the first slide so I can ask my question, that would be great. Thank you. Yeah, this one, for the performance. Now, I understand your definition of the wall clock time and the resource occupation time, and the thing that you said, where from the user end point of view, it really doesn't matter if the CPU is taking the time or the memory is taking the time. But it just seems very like kind of bizarre to me that we would have anything even for the CPU time, like we would care if the CPU is actually doing the work. So for example, this CPU is better than the other CPU. Do we have that kind of thing? Because I know that most of the time today, when we are having a latency or we are having a bad performance in some sense, it's because it's the access to memory that is bottlenecking our performance. So I'm saying, as an engineer, why would we ever care about a CPU time? Like, okay, this is a good CPU and it's doing its time perfectly, but what if the system in a whole view having a very bad performance because it cannot connect to its cache, the cache cannot connect to level 2 or level 3, for example, DRAM or whatever. And my point is that why would we have different kinds of even definition for the execution time, when in reality the whole system can be seen and should be seen as whole, because the CPU is not really our problem anymore, and there are other parts that we are missing and we have missed for a long time. Is that a true thing to think about, or is it like, no, it's still important to make sure that the CPU time is also being considered for some reason?
No, this is a very good point. And actually what you start to do is what I would say, consider, say, additional differentiation with what do we mean with resource occupation. Is the CPU occupied when the CPU stalls waiting for data coming from the memory, right? That's, say, a different way of how you could count it, because you could say, okay, I mean, and that depends also a bit on the architecture you're looking at, right? I mean, I might have an architecture where, or also a workload, where I can, while one thread is waiting for an instruction to be executed because the data is missing, another thread can start to be executed, right? So I would argue it still makes sense for me to look at, say, the resource occupation time. But of course, I also agree with you, it has to take, say, a holistic, say, view. So I cannot just look, okay, what was basically the time at which, for instance, the floating point pipelines were occupied, because then I would basically ignore, say, the picture which you were also describing, and where I would very much agree on that we are, say, in many applications just seeing, say, a very bad occupation of the floating point pipeline, because most of the time we're just waiting for data to come in. Right?
I would also add to the point that depends on the application how many CPU cores you can even use.
Yeah.
So if you have 1,000 seconds running in one workload time, it might be 4,000 seconds in resource occupation if you use 4 cores, or also 1,000 seconds running one core.
I mean, you could turn it even, say, a bit further around and say, okay, I mean, about which resource I'm actually talking here about, right? I mean, CPU time is just one example, right? And I will, say, later take you some examples where it is really purely about memory bandwidth, right? And so I don't care about how many floating point operations I can do, because I know my bottleneck is the memory interface, right? So I should rather look is what is the resource occupation time when I look at the memory interface. Yeah, so thank you very much for these questions. I mean, I think they are really very valid. Yeah, Stefan.
I also want to add that, I mean, it's also maybe a bit of a bad idea to disregard compute completely, even if it's much faster. And most of the time, memory is a problem, because, for example, the floating point pipeline may stall because it's waiting on memory, but the floating point pipeline can also stall because it's waiting on the floating point pipeline, because the algorithm wasn't written very well.
Yes. And there's certain examples, I mean, that's why I'm also trying to be cautious. I mean, it's just many HPC applications which are memory bandwidth limited. But if we, for instance, look into the molecular dynamics area, there are a number of, say, kernels which are, say, definitely, say, compute bound, right? And where it really is about how can I optimize the occupation of the floating point pipelines. So there is nothing like an easy right or wrong, and that's why I'm very happy about these questions, because they show that it's really about thinking about architectures in different contexts for different kind of workloads. But let's go back and to say this, say a more simple way of thinking about that, and I hope that this is helpful, and that is in the context of the latency bandwidth model. And essentially, it describes, tries to describe the time which it takes to execute, say, a simple, and that typically only works for rather simple applications, by looking at how much information do I have to change, which I encode here in a variable I, and I will define it a bit more precisely in the next slide. So it's really, say, based on the assumption that it is the data transport which is limiting myself. And if I go back and think again about this cartoon shown in the previous, so I mean, if I load, for instance, if it's about data transport from the external memory to the CPU, then I have to do first a request, and then it will take some time until the data comes back. So I will have something like, say, a kind of a startup latency, and so that is the time when, say, the event is triggered. That could be, say, the execution of a load instruction, until, say, the first data starts to arrive. And then once the data arrives, I mean, then it's essentially a matter of bandwidth, how quick this arrives. And so that is here in the picture. So I have this startup latency, and then at some point the data arrives, and basically the slope here. So the more bandwidth they have, the steeper the slope is, and if I have a very low bandwidth, of course, it will take more time for the same amount of data to arrive. So this is here as a function of the amount of data which has been transferred, which I call the information exchange. And I can write this then as a linear ansatz and say, okay, the latency delta t as a function of this information exchange is the startup latency lambda plus then this information exchange divided by beta, which is then, say, the bandwidth. And I mean, this model works surprisingly well. I mean, if some of you have a physics background, it's to some extent also a bit the naive approach of a Taylor expansion. So I start with basically a constant plus then a linear term, but often it is indeed, say, reasonable good starting point. And then I could have, say, something like an effective bandwidth, which is, say, the information exchange divided by the latency. And if I plug this into, say, replace this delta t here by lambda plus 1 over I get here what I call b tilde, which is here lambda over I plus 1 over beta to the power of minus 1. So what it essentially, say, this picture means is that if I transfer a lot of data, then this part can be, say, ignored, and I have just 1 over beta to the power of minus 1. So b tilde is equal to beta, so I'm completely, say, memory bandwidth dominated. But of course, if I transfer only a small amount of data, then of course this term becomes important. Now, another, say, little thing that I want to convey in this context is, I mean, we started with this ansatz, and we can, say, in a picture, say, show it in this way. If you look instead of delta t versus I versus delta t, if you would now look at that is essentially b tilde versus I, then we see here a much more complex relation, right? So because here we are latency dominated, and the larger I is, we essentially get here to the asymptotic bandwidth, which here is assumed to be 1. Now the takeaway message here is, if you would just measure, say, the bandwidth as a function of I, you might see something which is rather complex. And my experience is, in many cases, it's just simpler if you, say, just say plot the execution time, because then it's a much easier functional form. There are exceptions, I mean, where it still also makes sense to look at the other picture, but keep in mind that you might look at something rather simple, but if it's the inverse of something simple, it can look rather complex. Now, let's look at what actually mean with the information exchange function. So essentially, the idea behind the information exchange function is that we think about the computer as a set of storage devices, and we move data between the storage devices. Right? I mean, it could be, say, simple architecture where I have, say, a processor core with the register file and then external memory. Then I have the register file and the memory as 2 storage devices, and I move data between them. And there is this information exchange function which says, okay, I move for a particular computational task K, I move data between X and Y, and how much data I move may also depend on what is my the workload, so what is my problem size. I will give you some specific examples, right? But generally speaking, if I can analyze my application by really determining this information exchange functions, I gained already a lot to be able to understand actually the performance. But admittedly, depending on what kind of application I look at, it can be kind of complex, but I will just give you some easy examples. But let's first look at what is the thinking behind that. I mean, it's really of looking at computers in the most abstract way and say, okay, I mean, my computer is a set of interconnected devices, and essentially it's mainly about storage devices. And the connections are, I call process or transport devices. And so this is essentially, say, the picture shown before. I have the external memory, I have the core, which is just with a register file, and they are connected by a transport device called the memory bus. And then from the register file, I have some, could be floating point pipelines connected, which take something out of the register file and moves it back into the register file. So that also means that this very simple thinking about computer architectures gives me also a very simple graphical representation. I get a graph where the nodes are the storage devices and the edges are then the transport or processing devices. Now let's look of how this works in practice and keep it, say, in a very simple case where we use this ansatz before, where we have, say, the latency, the startup latency, and then the information exchange divided by this asymptotic bandwidth. And now we could, for instance, have the simple case where we have, say, just a register file and we move things here through an execution pipeline. So then beta would be the throughput through an arithmetic unit. Right? Of course, it's a very simplified ansatz, but in many cases, I would argue it works reasonably well. Now, let's apply it to something a bit more realistic one. Not as complex as the DuxP already introduced, but something even slightly bit more simple. We say, okay, we have two arrays x and y, and we multiply each element of x with a scalar alpha, and then write the result to y. So now here we have, we can define here two information exchange functions. One is a consequence by having to load each element of x and to store each element of y. I make here for the time being the assumption that these are very large arrays, and that I hope that my architecture is smart enough that I can do the optimization, that I can keep this scalar variable in my register file, so I don't have to move it between memory back and forth because it's just a constant. So now I can say it's rather straightforward to understand of how much information do I exchange between my external memory and my processor. I just have to count. Now if I say, okay, these are single position floating point numbers, so 2 bits or 4 bytes. Then I have to load x and to store y. That gives me 4 plus 4 bytes, and I have to do it n times. So the information exchange function related with loading and storing x and y, which I call IMEM, is just 8 times n byte. Okay, now once x is loaded into the processor, then I have to, say, move it through some floating point pipeline. So I get the second information exchange, which is, say, related to the multiplication of x by alpha. And here I'm just doing one flop. So I have now a second information exchange, which is called IFP, is n times 1 flop. Okay, so now I have to essentially characterize my admittedly simple application. But I would argue in a reasonably powerful way, because now I can start to reason about, say, architectures and start to say, okay, let's assume that I have an architecture where I can move 1 byte per clock cycle, and I can do 1 flop per clock cycle. Just a warning, advanced warning, I just did it for the simple numbers. It's not particularly realistic, because if I would have this architecture, it would be very nice. I see a number of people smiling and knowing that that's typically, I mean, you would have, say, a much higher throughput of floating point numbers versus the available memory bandwidth, right? But still, even in that case, the prediction would be that if I would, say, just use this information exchange, this beta mem, and ignore the startup latency, the prediction for the latency delta mem would be n times 8 clock cycles. And so it's just imem is n times 8 bytes, divided by beta mem is divided by 1 byte over clock cycle, right? So it's 8, n times 8 divided by 1, and then bytes, they disappear, and I just have the clock cycle, so I have just n times 8 clock cycles. And the mask for delta t fp, where I just divide IFP by beta FP, again I ignore this lambda FP, I get just 1 clock cycle. So what essentially this very, say, back of the envelope analysis tells me, okay, I would, even in this, say, architecture where I have a pretty high memory bandwidth, I would still spend, say, more time on actually, doing the data transport. Now the question is, how can I actually make an estimate of the overall latency, right? Because at the end, I both want to load the data and I want to do the floating point computations. Is the answer now that I have to add these two because these two things don't overlap and I would end up with n times 9 clock cycles? Or do these two things perfectly overlap and then I would have the maximum of delta t mem plus or delta fp and I would have 8 clock cycles. Yeah. But whatever I do, I mean, obviously the conclusion is I'm having here a memory bandwidth limited problem. And I can, say, take this analysis a bit further, and that's, say, something which you can also find in literature. I mean, the other analysis that I introduced before is not that common. But I will show you that we can derive from here something which is pretty well known. And let me first introduce, say, a notion which is called arithmetic intensity. Meanwhile, it also has become popular to call it operational intensity. And it essentially means that I, in the numerator, count the number of, typically the floating point operations, and divided by the amount of data which has to be transported. Now, recall what we introduced before with the information exchange. We can very easily give this a very concise definition. It's just IFP divided by IMM. So if you just go back to our previous example, where, say, IFP was n times 1 flop, and IMM was n times 8 bytes, n drops out, so we have, for this specific operation, we have an arithmetic intensity of 1/8 flop per byte. And if we would have used all precision numbers, then it's very easy to of course, we have to move. We still do 1 flop, but then it's, of course, a different kind of flop. But we have to move twice the amount of data. So we get even, say, in units of flop per byte, we get even a lower arithmetic intensity. Now, this notion of arithmetic intensity has become, say, very common. It's a very typical way of how to analyze applications and this comes also because of, there had been a model which has been introduced, which is called the roofline model. And I will, say, try to derive it here in this one slide, and it goes back till, I think it was still at that time a master's student, or it was already a PhD student, but in the end of the 2000s. And essentially, we start with saying, okay, I mean, let's look at the effective bandwidth, which is essentially the amount of, for instance, the number of floating point operations divided by the latency, right? So that gives us, say, the effective throughput of floating point operations or the effective bandwidth. And now say, okay, we have for our architecture, we have, say, for that an upper limit, because we know that there's a peak performance. There's no more floating point operations which we can execute. And the same if you look at the data rate on the memory bus, whatever you do, you can't be so it's a kind of speed of light thingy. So you can't be faster than, say, the data rate which is offered on your memory bus. So now if we say assume that, and that's where the roofline model is very much based, and that's of course an important assumption. If you assume that the data transport to the memory and the processing of the instructions can be perfectly overlapping, then we could write delta t is the maximum of the number of floating point operations which have to be performed, divided by what is now, say, essentially the achievable effective throughput of floating point operations. Right? And if you are memory bandwidth limited, we essentially say the maximum would be the amount of data which needs to be transported divided by, say, the effective memory bandwidth. Now, because of these assumptions here, we can say, okay, this maximum is greater or equal than if instead of having here BFP, we have capital BFP, where BFP is essentially kind of an upper limit for our given architecture, right? And the same is for BMEM. Right? So now we have here a kind of a lower limit, so a delta t, so our latency, is larger or equal than the maximum of these two terms. So now let's look at how we can from this derive a kind of an upper limit for our performance, and more specific for our floating point performance. And we can do it by, say, writing, okay, our floating point performance is the number of flops which we have to execute divided by the latency. Now for the latency here, now we can here, say, plug this in and say, okay, we know that the latency is larger or equal than maximum of this. Now if you put now the delta t here in the denominator, the larger equal becomes smaller equal of the minimum. So from this we can say it's just an algebraic transformation to get here as a minimum. Now we have here, we have IFP divided now here by IFP over BFP. So IFP drops out and we just have BFP. Is that clear? So we have IFP over BFP, right? And then, so it's only BFP is left. Now here we have IFP divided by IMEM, which is just arithmetic intensity, right? So we have IFP divided by MEM, and then BMEM comes in the numerator. So what we have here is now, we can now say the maximum attainable performance is smaller or equal to the minimum of the maximum throughput of floating point operations, or the arithmetic intensity like the maximum memory bandwidth. And essentially, this inequation is called the roofline model. And why is it called the roofline model? Because it has a very nice graphical, say, representation. And that is shown here. What you see here in this blue curve here is essentially showing what is the maximum attainable performance for a given architecture as a function of the arithmetic intensity, where if the arithmetic intensity is, say, very large, if this becomes very large, at some point arithmetic intensity like times BMEM will become larger than BFP. Right? So at some point BFP will be the largest, and that gives us basically a flat roof. If the arithmetic intensity is very small, then this will be the smaller out of these two terms. So the maximum attainable performance will be essentially determined by arithmetic intensity times BMEM, and will then be a function of the arithmetic intensity. Right? And that's why we have then here this slope. And this slope here is essentially, it depends on the memory bandwidth, and that of course depends on the architecture. Now, one of the things more from a real theoretical perspective why I like this picture very much is the blue curve is essentially completely determined by my architecture, right? This is the maximum throughput of floating point operations. The slope here is the maximum memory bandwidth. But the arithmetic intensity is a feature of my application, not of the architecture. And if you now get back to, say, the case, and these are reasonable, realistic numbers which I put here, what you will typically see, and of course that's now a bit architecture dependent, what you will typically see that's now the scaling of a vector is just down here. So it's really here in this part over here, and that's what, and this whole region here, that is the memory bandwidth limited region, right? Because that is determined not by the maximum throughput of floating point operations, but by the maximum memory bandwidth. And only if you would have an arithmetic intensity now here of more than 1, where we would be limited by the floating point throughput. So that's why when you analyze, say, an application, it's always a good thing to try to get at least a rough estimate of the arithmetic intensity, because it's something very powerful, because it tells you something about where could you be limited. Any questions so far? If not, then the second part will now be much more practical. And this is now how do we actually measure performance? So this is now less about theory. Now, measuring performance, well, there's a whole field which is, say, keeping itself busy with, say, doing all kinds of tools for measuring performance, because it's not that trivial, in particular when our application becomes, or our architecture, sorry, become very complex. And there are different ways of doing it. I mean, you could, for instance, do some profiling. That is the most popular thing. So basically you aggregate some performance metrics and then you store the aggregated figures, right? For instance, what is the average time spent in a subroutine, right? So at the end, it's not so much information which you, I mean, you collect a lot of information, but then you compute an average number, and at the end you have just one single figure. Now you can also do things a bit more sophisticated and say, okay, I do kind of a sampling and say, okay, I mean, I, for instance, regularly ask my architecture, okay, how many floating point operations have you, for instance, performed, right? And then randomly get at discrete time points, I get information of what is actually going on in my. Of course, I get here now more, say, data, but it also has some of the benefits that I can, say, independent of the application, do that. But there's also something which is called event tracing, that in case there are certain events, I enter a subroutine, I exit a subroutine, that I collect information, I add a timestamp to that, and then afterwards I process this information. Now, in many of these ways of how to do performance measurements, I have to, of course, do some, say, additional work on my CPU and actually collecting this information. And in many cases, I actually have to what is called instrument my code. That means I have to modify my code, say, okay, please at this point look at, say, start to trigger a stopwatch, and at this point say put the stop on the stopwatch and store the result, right? So in some sense, there is, depending on how I measure performance, there is a risk of distorting what I'm doing. Now, one of the nice things is that in the last decades, and that's part a bit of the consequence of Moore's law, that you have sufficient transistors available, that I can also add to my CPU architecture, say, functionality which supports the measurement of performance. And what now even simple processor architectures do have is, I mean, it's often called in different ways, but I prefer to use the term performance monitoring unit, which can be very simple. It's essentially, say, say a counter which I increment when a certain event occurs, right? So an event might be a clock ticks. So then I can just use the counter to measure time. But an event could also be whenever, say, a floating point instruction is being executed. If that happens, please increment this counter. And then afterwards, the CPU can tell me exactly how many floating point instructions have been executed. Now, this might not be necessarily so interesting, but for instance, if I think about caches, that's a bit more difficult to actually understand of how many cache misses had there been. Then it's good to have these kind of performance measurements units. Now, there are some issues. I did already mention the issue. If I have to do instrumentation, then of course, I change my application. And in the extreme case, I change the application in a way that the performance characteristics are completely different. So I have information which is in some sense useless. Now, also the accessibility of the hardware counters can be a bit tricky. I might have to have support from the kernel, so security has become more strict. So typically you have to already, say, tweak the Linux kernel configuration. So typically a runtime parameter such that I can actually read that. But I may also have, for instance, issue with managing, say, for instance, large event traces. Think about a parallel application which is running on 10,000 of nodes and they all collect data. I mean, I quickly would end up with terabytes of data. How do I process that, right? So it becomes a big data problem. So there are, say, some issues there. But there are also some more practical issues, and here we won't, say, bother about, say, measuring things on 10,000 of nodes, but keep it more simple and look just at a single node. But still also there we have to look at what are the timescales when we just want to measure time. Now, if we are, say, on a processor which is running, say, at 3 or 2 gigahertz clock, then it means our clock cycle is 300 or 500 picoseconds. Right? So it's a very small time scale. And now, if you recall that we have, say, L1 access with, say, about 5 clock cycles, we are at the nanosecond scales, right? And that is also, even if you have here 2 orders of magnitude more time for actually accessing the memory latencies, I mean, we are still, say, at the dozens of nanoseconds. So we need to be able to measure, ideally we would like to measure much more precisely than, say, less than a microsecond resolution. So it's about doing very fine time measurements. Now, if you just, say, ignore, say, all these different, performance tools which are available, and in practice, I mean, I admit I often do it because getting the performance tools to run on new hardware is often a problem, but often, say, if a new architecture becomes available, at least Linux works, and then I can use basically just standard Linux commands. I mean, you could in the extreme case still use, say, user bin time, and thus with your command, but it's not recommended because typically the resolution is given in ticks per second, where you use the system clock, which is 10 milliseconds. So it's far away from the microsecond resolution. But some cases it can be good enough. What actually is quite nice is to use clock dead time, which say gives a bit more complex structure, but in principle gives you, say, the information down to the nanosecond resolution. But you can also query what is the resolution there. So this is actually quite useful function which is available in any standard libc. Right? So this you can always use. But of course this is just measuring time, and that's we would like to be able to do more. And there is a very nice performance tools which unfortunately seems to be continued to be developed, and Stefan has put, say, the most recent versions on the cluster. So that's why I had to update my slides. But actually they became simpler. So PAPI has actually quite some history. It stands for Performance Application Programming Interface. And it's, was originally mainly developed at the University of Tennessee. My impression is it's meanwhile, in particular also CPU vendors contributing to this. And it is, supported now in quite a number of architectures, not only, Intel Xeon, the AMDs, IBM Power, but also, various ARM processors, including the Comping 920. And the basic idea behind that is, these performance measurement units, they are not standardized. So that means each vendor does, its own thing, right? So it has its own way of how to program the performance management unit. The addresses are, all different. And just a simple idea with PAPI was to say, okay, let's assume all processor architectures allow us to count the number of clock cycles. So we just define an API which allows the programmer to say, okay, I want to have the total clock cycles, right? And now let's just leave it to the library to knowing on which processor architecture it's running to select, to do the right thing in order to get the total number of clock cycles, right? So in some way, by using this library, you become portable because whether I ask for PAPI cycle on an Intel Xeon or a Comping 920, it's essentially just the same, right? And it's the library which is supposed to do the right thing. Now, it's not only about looking at clock cycles, you can also look into, for instance, what is the total number of instructions which have been executed, or look into some of the details, what are, the number of floating point instructions which have been executed. Very interesting is typically also to look into the number of cache misses for the level 1, level 2, and level 3 cache misses. Now, one warning particularly here, I mean, PAPI defines, say, that you can, say, access these kind of counters, but it doesn't guarantee that these counters are available, right? So you may be unlucky and find out, okay, I would like to have the level 1 data cache misses, but unfortunately, I can't access them. Well, level 1 will typically be available. Level 3 is a bit more interesting because that is it's not linked to a single core, but it's linked to basically the full CPU or the chiplet. For some applications, it might also be interesting to look into the branch instructions, or when you have a branch predictor of how many of the predictions have been mispredicted, right? So then you can basically get a lot of dynamic information which otherwise you would not get. Now, just to be very practical, and you can try it out later on the cluster. We should, before we start into the hands-on, make sure that we circulate the link to the GitHub repository where you can find a copy of the slide, so you can just reuse what is shown here. We say the most recent version of PAPI, instrumenting the code, and in some sense a bit of a disadvantage of PAPI is that you have to explicitly by hand instrument your code, but it has now become very simple. What you essentially have to say is, here there is a region where I want to perform, here a region starts where I want to perform measurements, right? So I just call a PAPI, that is the HL stands for the higher level interface, region begin, and then I give it just a label, an identifier. So I call it here kernel. You have called it people, right? That's also perfectly fine. It's always good to check whether the call to the library worked well. So I check here whether this function returns something which is equal to PAPI OK. If it's unequal to PAPI OK, we end here. So now next we start some kernel. So we do some work on, let's say, the part where we are actually interested in, so where we do the measurements. And I did here something which is not too simple, because otherwise the compiler does a few strange things. So I just read from an array A, add here a constant, and then store it back into an array B. Right. So I execute this kernel, and then I have to just, the complement of begin is end, and I have to make sure here that, of course, these two references do match. Right. And that's all. So that's all the changes which I have to do with my code. So that has become, say, rather simple. Now, here I don't say anything about which counters do I want to access, right? So how do I do that? Well, this has become essentially be delegated to runtime. So what I now have to do is I compile my program. I assume that the C code, which was shown in the previous slide, is, say, stored in a file example.c. And I call now GCC as compiler, and the output of the binary generated by GCC is called ex.x. And now, in order for these functions, which I use the PAPI functions to be found, I have to give here, say, the option -l PAPI, so I link with the PAPI library. By the way, I didn't explicitly say it, but of course you need here also for these functions to be declared, you have to include here papi.h. So now I have an instrumented source code, and then an instrumented executable, which is linked to the PAPI library. Now I have to execute it. Now before I execute it, I should, say, define two environment variables. One is the PAPI output directory. That's where the measurements are going to be stored. And I say here, okay, it should just be my local directory. And then I have a second environment variable, which is called PAPI events, and where in a comma-separated list, I now write the events which I want to measure. Now, one thing to be careful about, actually I didn't test of how now the new API reacts. Typically, I cannot measure too many of these counters in parallel, because remember we are talking about a performance measurement unit which just includes a number of counters, and of course the number of counters available there is limited, and it depends a bit on the implementation, so there's not a guaranteed number of counters. But it's reasonable to assume that 2 are there. So what I do here is I ask here, when my application is executed, measure the total number of cycles in this region which I defined before, and measure the number of load instructions. Yeah? And now the only thing which I have to do is execute. So when I execute that, what I will find back, and you can try it on the real hardware later, is I will find that there's a subdirectory created, and this subdirectory there's a JSON file. And in this, and I showed you here, I just run this in the last weekend on the Kubernetes cluster. You can see here that's a brand new version of PAPI, version 7. You see it also provides some information about the CPU in which it was executed, so that's nice. It's the high silicon Kunpeng. It also shows me about, okay, what are the events which have been measured. And it gives me even, say, some information about how they have been measured. So it actually was not using, in this case, directly the performance management unit, but it actually went through the kernel with the perf events. I will introduce perf next. But the more interesting part comes now here, is here, you can see here, again, the string back kernel. So I said, okay, please measure, say, performance for a region, which I call kernel. Again, I could have called it people or whatever I like. And here I find information about the counters. So I see that here in this case, it's a little bit more than 100,000 clock cycles, which are required to execute this kernel. And I did a bit more than 60,000 load instructions. Okay, so this is now our measurement. So now start to do our analysis. And now let's look into these numbers, and I will focus just here on the load instructions. Now, we had in this example, which I was given 2 slides before, I had put this n, so the size of these arrays, and therefore, say the time the loop is executed, to 10,000. So now, Papi told us, okay, when I execute it, I mean, it's a bit more than 60,000 load instructions which are being executed. So if I divide it by, say, the number of times the loop is being executed, then I get, so this is n load divided by n is about 6. Surprisingly large number, but if you look in the assembler, and so this is the assembler, and just to anticipate, say, the next slide, this was not compiled with optimization, so it gets pretty complex because the compiler doesn't do much optimization. And if I just count, I have a load here, 1, 2, 3, 4, 5, 6. So again here, sorry, I should have said, here again I have here, say the compare, and this is now not SVE, and here I have the browns if less than equal, so this is basically, that is my loop body here. And I have, inside this loop body, I have 6 load instructions. So I can essentially, say on the one hand, I could have, say, looked into my assembler code, and could have seen that I need quite a lot of load instructions, but also say the performance counter measurements actually allows me to get there. I mean, I like to do this kind of experiment, even so I know that I could just say go through the assembler. It gives me, say, some kind of consistency check, so to make sure that I do the measurements right. And by the way, for those who don't know of how to generate this kind of assembler, just call GCC with minus capital S, and then have here the C function, and then it will produce a file called ex.s, and that contains exactly the assembler which is shown here, right? So there's no handwork. That is basically all automatic work. So now anticipating a little bit, say, also since we also want to think a bit about optimization. I mean, if you look into this C code, I mean, this is the kernel which we do here, right? And in principle, the only thing which we want to do is we want to load A and to store B, right? So why the hell do we need 6 load instructions? Right? So in some sense, I mean, doing this performance analysis also gives us a bit of an idea of what could be optimal performance by saying, okay, I mean, if you look at our code, I mean, we wouldn't like to have this lowercase n to be 6, but rather to be 1. Now, fortunately, in this case, we can do a very simple optimization. And the simple optimization is just put O3 here in the compiler. And now we just, I just renamed the executable here. So that's also there. And what we get here now is, well, instead of having, say, more than 100,000 here, we have 40,000 here in terms of the number of clock cycles. So it went faster. But also what is nice to see is now before we had more than 60,000 load instructions. Now we have 6.3 thousand. Okay, now going back into the analysis, if we now again do the same thing as before and we divide it here by the number of loop counts, we are now suddenly with 1/2 load instruction per loop iteration. And before we said by inspecting our C code, we would expect only 1 load instruction per clock cycle. So does anybody have an idea what could be going on here? So why are we suddenly doing much better than we expected?
The code is vectorized.
Exactly.
Instructions.
Yes. Yeah, it uses.
Times the data by 1.
Yes, exactly. So it's the vectorization which kicks in here. In the second lecture, we will look a bit more carefully into the auto-vectorize of the compiler. But by using here I anticipate this already here, by putting, in case of GCC, if you put O3 here, you tell the compiler, please also try to vectorize the code. And this is, not necessarily so easy to actually see here, but this is actually, say, the assembler which had been generated. And you can here also see here in the labeling of the, I mean, you can't see it here in the instructions, but you can see in the labeling of the registers that indeed vector register or neon registers are being used. So in each clock cycle, instead of just using, say, doing 1 load, it does 1 instruction which does 2 loads, right? And that's why we only need half the number of loads. Right? So I hope with that I could convince you that with these kind of counters we can actually, say, get a lot of information and learn something, even if I have a very simple application. Now, of course, you not always do want to instrument your code. I mean, the code can be very complex. So there's also other ways. I mean, there's, for instance, a tool which can be reasonable, okay, but you have to be a bit careful how to use it. It's called perf. It's actually also available as standard Linux. And so if you say call perf and do list, then it lists all the events which are available. And it can have more or less all the events which also say are available in PAPI today. So in this sense, it's not so much of a difference. And you can then call perf stat and then the executable. And then it will run the executable and doing the execution collect statistics. And if I don't do, say, any additional, use any additional options, it will just come with some standard information, which includes also, say, for instance, the number of clock cycles, the total number of instructions, right? But I could also have, say, used some options in order to get the number of load instructions in this way. Now, you may have remembered that before, with measuring with PAPI, we got something about the 100,000 clock cycles, and now we start to have many more clock cycles. Do we have any idea of why there could be this huge difference? Yeah?
It's also running there?
No, that should have too much impact. That shouldn't have too much impact because at some point you just spawn basically the say the second thread which is executed in the application, and perf should be more or less in the background. That's probably not consuming. Now the answer is simple, that I now have, say, I'm running here now the full application, and there's I/O involved in there. So that is causing, before I was just measuring, say, the time which is spent in a kernel in a well-defined region, right? And now I have from the very start of the application to the very end. So this is something I need to be aware that I might have, see a lot of overhead. And one trick to get away of this overhead is, for instance, to repeat the measurements for different array lengths there, right? And then I can just subtract the overhead and then get an estimate of how much time was spent in the kernel. So I'm measuring here not just the loop, so the kernel, but I am measuring here much, much more. So the final part of this lecture, let's now look into, say, a bit more sophisticated performance tool. And we will use it here not for the full sophistication. I mean, it was originally developed in actually being able to do measurements for complex distributed MPI parallelized programs. And it was developed mainly in Jülich, and then one of the, or the main person behind it went, Felix Wolf, into the Technical University Darmstadt. But it's now, also to be fair, it's now also based on, say, software layers which are now developed by international collaboration of people, and I will mention it more explicitly later. But the nice thing is it's open source, it supports different kind of platforms, it supports different compilers, and it's essentially based on an approach which you also find in other performance tools, is you start with essentially doing the instrumentation while you could still do it in hand. You typically do it by a tool. So it's the tool which does the instrumentation. You don't have to do the instrumentation yourself anymore. And then you do the performance measurement during execution. So it's a little bit like we did before. And then we have additional tools for analyzing, say, the performance. Now, let's go through these 3 steps. The first step is the code instrumentation, and this is actually, say, something where, say, the developers of different tools, I mean, there's Scalaska, there's Tau, there's Vampire, and they at some point notice, oh, we are essentially all repeating the same thing. We somehow try to have tools which allow for automatic code instrumentation, so why don't we work together and generate something which is now called SCORE-P. So SCORE-P is basically a framework or an infrastructure which you can use for all these different measurements, and then there are different tools which sit on top of SCORE-P. And if you want to instrument the code, so I called now our example where I removed now these calls to PAPI, but otherwise it's essentially the same code, but I just called it then now example no papi.c. I basically have here the same way of how I, say, do compiled it ex.c. Without the O3, I again say, okay, this is now my output. The only difference is now I put here a tool in front of it, which is called skin, right? And skin essentially takes this command, but does some other magics, which results in an instrumentation of the code. Essentially, it looks whenever is there a function call, and whenever I jump out of a function, then it will insert some instructions which will result in measurements. Now, it's important to understand this a little bit, because if I have a code, and that's particularly an issue for C++ programs, where I have a lot of very small functions, the code instrumenter might start to inject a lot of code, and that can distort things. So it works well if you have big functions and not too many functions, but otherwise you have to tweak it a bit. But this is a level of detail we won't enter here. Okay, now we have an executable, we're happy, instrumented, so we haven't put anything into our code like before where we had the call to PAPI, nothing like that anymore. And now, like in the case of perf, we have to execute it using a tool. And in this case, the tool is called scan. So I do scan, and now I call my application in the way as I would call it in a standard shell. Right? And then it gives me, say, some output, and the most important thing is it gives me also here a directory in where the output is stored. Right? So I get here a subdirectory in a new subdirectory. And if I just do it in the way as it's shown here and don't do anything else, then it would, for instance, provide me with timing information. Now, you can actually also link this with PAPI, and Stefan fortunately built it in the way that PAPI support is there. And then the only thing which you have to do is now, and that's very similar to PAPI, that you have now to define an environment variable, which is called here scorp metric PAPI. And then again, I give him as a comma separated list the PAPI events which I want to measure. And then I can again say, now I have to recompile and then re-execute, and then I will get the PAPI counters. Now comes the third step, and so the last step, and that's also the last slide. Now I want to analyze this data. And if you like, the nice thing, and that can be, say, indeed nice if I have a more complex program than I had before, is that now I have also, I can use, say, the command line interface called kubestat, and then I can use everything on my terminal, but I can also use a graphical user interface, so a GUI, which is called Kube, and that's how I called it, and it's now for this measurement, exactly for this PAPI example. And as you can see here, I didn't have to modify my code, and now I can here, for instance, count here the number of load instructions. So I did the same measurement as before, and indeed, I mean, this is now the non-optimized case. I again have back this slightly more than 60,000 load instructions. Right? So I did not have to instrument my code, and I just have to invoke a graphical representation, and I can say, if you like, more easily see what is going on, right? Because I might have a much more complex application, and there might be a lot of subroutines, and not just this very simple where I have only one subroutine. So in this way, I could, of course, here easily navigate to a complex program where I have a much more complex call tree. So that was the last slide, and again, I want to finish with a picture. Actually, I decided this time to go back in time, so I started with a very recent architecture. I always like to show this picture with the Enigma architecture from Turing or Bonn, because it reminds me a bit that high-performance computing has a lot to do with military research. So still, as of today, if we wouldn't have this military research, in particular, say, the nuclear missile simulations, we wouldn't have, say, the high-performance computing systems. I think that's a fair prediction. And a lot of the development of, or the speed up of the development of computer architectures in the middle of the last century was driven by, say, the military needs during the Second World War. That was, in this case, the decrypting of, say, what the German military was, say, communicating. And so that was resulting in one of the early, say, real working supercomputers at that time. And that was, say, quite successful. Okay, with that, thank you very much. I have further questions.